Hey guys, Mr. Newman here, and today we're going to learn about geometric sequences and series. It relies, or it looks very, very similar to 9.2 because it has a lot of the same vocabulary, just a few differences, especially at the end. So, first of all, a geometric sequence is a sequence that multiplies or divides to get to each next step, where versus an arithmetic that adds or subtracts, we have multipliers or divides. And you can multiply by a fraction, so you could simplify it to just being multiplying all the time. For example, in this one, we're always multiplying by 2, and that is the common ratio. That's the amount that the geometric sequence multiplies by each step. There are two ways to find this as well. I prefer the first, of course, but I'm going to also show you guys how to use a formula. Very similar to the last one. We're going to make a table, and just like the last one, we're going to use step as our x and number in the sequence as our y. I'm going to actually pick a different sequence. I'm going to use this one right here, the 3, 6, 12, and 24, just to illustrate a few points. And so let's put the steps in 1 through 4, and you notice I left a little space to the left that is blank. You can probably guess why. We multiply this by 2 each time to get the next step. And so if I write these out kind of vertically, you could write the first step as 1, second step as 3 times 2, third step as 3 times 2 times 2, and the fourth step as 3 times 2 times 2 times 2. Well, if we write this out, that's like 3 times 2 squared. The previous one's 3 times 3 cubed, 3 times 2 squared, 3 times 2 to the first, and 3 times 2 to the 0 is another way to think of each of these. So if I try to write this as a formula, f of n equals 3 times 2 to the n, this is actually incorrect. And be very careful about that, primarily because a few reasons. If you try plugging in 1 there, for example, you will not get 3, which we need to get 3 if we plug in 1. If you plug in 2, you will not get 6. The main culprit is this 3 right here, because we're not really, like, the sequence starts at 3, but as a function, it doesn't really start at 3. So just like before, I'm going to go back and think about step 0. If we go back a step, what times 2 equals 3? Well, 1.5, or 3 halves. It's a little smoother to write down the fraction 3 over 2, and then you'll see that more in math class, but I'm going to go ahead and use the decimal form right here for now. So the formula is actually f of n equals 1.5 times 3 to the n, and that gives you all of those steps and all those sequences, numbers in the sequence. That's our answer. How you can find it using the formula, if you notice the n minus 1 up there, that n minus 1 is our way of kind of taking a step back, just like the n minus 1 in the arithmetic sequence was our way of taking a step back. So a sub 1 is the first term, that is 3. And r is the common ratio, that is 2. So we get the formula 3 times 2 to the n minus 1. Now, for those of you who are wondering, like, wait, that doesn't look like the same formula. It actually is. Let me do a little bit of math and show you why. You guys know when you have a number to a power, that's the same as adding those numbers or multiplying not the denominators, the bases. So that's the same as 3 times 2 to the n times 2 to the negative first, right? Right. Well, that 2 to the negative first is the same as 1/2, and when you rearrange those and multiply them in a different order, 3 times 1/2 is 1.5. And look, whoops, we got the same exact formula. So they actually are equivalent formulas, and you'll see both in these situations. All right, a geometric series, just like an arithmetic series, is when you add all the numbers up of a geometric series. I think they're a little bit more fun than arithmetic ones because they lead to some really interesting results. And I'm going to show you a few cool examples in class. So, first of all, with this formula, you need to know that S stands for the sum, just like it did in the others. That is summation notation, so you'll often see them written like that instead of them written all the way out. And the formula is right here. A sub 1 times this fraction, 1 minus r to the n and over 1 minus r. Now, a few things. Notice, before I get too far, notice right here the r to the I minus 1. Okay? That is, remember, using the formula, the step back, that n minus 1 or I minus 1. So be aware of that if I give you a generic one where you need to actually figure out what n and I are. All right, so how in the world do we apply this? Well, what you have to do is you have to identify each of the parts for the formula. So for example, a sub 1 is that first term right there. That's the a sub 1 that comes from the formula. And so 4 is our first step, 4. In the parentheses, we have 1 minus r. R is the common ratio. Well, that shows up right there. That's the base of the exponent. So r is 0.3. So I'm going to write 0.3 there. N is shown over here at the top of the summation symbol, the sigma symbol, and that is going to be 12. And then on the denominator, we just have 1 minus r, so 1 minus 0.3 again. When you do all this, you can actually type that into a calculator, and you get something like 5.714. Now notice the squiggly lines because I'm approximating it, and for these, that is what you'll want to do. The next one, that we call that a finite formula because that's listing out all the numbers starting at 4 and multiplying by 0.3 all the way up to the 12th term. An infinite geometric series actually keeps going on forever. So, for example, if I write this one, if I write it out like this, it'd be 4 plus 4 point, oops, let me write it a little faster, 4.3 plus 4 times 0.3 squared plus 4 times 0.3 cubed, dot, 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 all the way to 4 times 0.3 to the 11th, because n is 12, and we need to count the first one. So that's how many terms there are. Well, that is great, and that's a finite series, but what if that kept going? What if we cross this out, and we just put dot, 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 like those keep on going forever? That actually sometimes adds up to infinity, but a lot of times, especially when r, or always when r is less than 1, it will add up to something that converges. In other words, it stops getting bigger and bigger, and we get a finite number. Pretty cool, huh? So the other crazy thing is in this infinite formula, or for the infinite formula, it's just a sub 1 divided by 1 minus r, which is a really, really simple looking formula, especially when a sub 1 is 1. And there's some really cool situations I'm going to show you guys in class of how to apply that. So here, let's do this example for this one. Notice it's an infinite sum. So we have a sub 1 is 4, and r is 0.6. So what I'm going to do is I'm actually going to solve this without a calculator to show you it's exactly equal to something. 4 divided by 0.4, well, let's see here. That's a fraction. Dividing is the same as multiplying by the reciprocal. The 4's divide out, so we get that whole thing, if you keep going with that, adds up to exactly 10. Now that's almost the same as this one up here, except for replace the 0.3s by 0.6, but that adds up to a nice, neat number. Kind of neat, isn't it? All right, thank you for watching.